Okay, so the question we're going to do here is assume that the significance level is alpha 0.05. Use the given information to find the p-value and the critical value or values, plural. The test statistic is given, and it is obtained when testing the claim that p, a proportion, is greater than 0.9. The p-value is what we're going to look for, and the critical values. So normally in a problem, we would be doing more steps than this. So this is kind of like boiling it down just to the sketch part of it. So they've given us the alpha, which is the area that goes with the critical region. Yeah. Well, let's start with the claim. The claim is that P is greater than 0.9. And that means that the null hypothesis and the alternative hypothesis would both use the P and the 0.9. The null hypothesis will always use the equal sign. And if there's no equality in the claim, so if the claim has either this symbol, or this symbol, then it will be your alternative hypothesis. So because there's no condition of equality anywhere in the claim, it's our alternative hypothesis. And that tells us that the sign here on your alternative hypothesis will tell you the tails for your test. So because that's a greater than symbol pointing to the right, this is a single-tailed, right-tailed hypothesis test. So our critical value is going to be the boundary here, and the alpha will be completely contained in one tail at the given 0.05. Does that all make sense to you so far? Yeah, because there's no condition of equality in the claim. If there's any equality in the claim, then it gets sucked into it gets covered by the null hypothesis because the null hypothesis has equality in it. And the null hypothesis is one hypothesis. The alternative hypothesis is the other. So they can't have any overlap, if that makes sense. So anytime that there is equality mentioned in the claim, like if it had said the claim was that P was greater than or equal to 0.9, then yeah, the null would still be P equals 0.9, and that would cover the claim because of the equality part of it. And so then your alternative has to be the complement of the claim. And so then it would have been a left-tailed test. Correct. So it always goes that either your alternative hypothesis is the claim if it has no equality in it, or if it does have equality, then this has to be the complement of the claim. So in this case, the claim had no equality. It was a strict greater than, no equality there at all. So it became our alternative, and we have a right-tailed test. Right. And the claim is falling under the alternative hypothesis. It's always the symbol of the alternative hypothesis. Whatever that symbol is will tell you which direction. So if you have a greater than symbol like we do here, then everything's on the right. If you have a less than symbol, then everything would be on the left. So that would be a left-tailed test. And if it's a not equal to symbol like this, then it's two-tailed. Yes. Yes. Okay. So that's why it's so important to start with the claim so that you can make sure you know what kind of tails you have. So now that we have figured that part of it out, we can find the critical value, which is one of the questions that we have to answer here. So notice it says critical value and then in parentheses with the S. So what that means is it could be a single critical value for a right-tailed test or a left-tailed test, or it could be two critical values if it's two-tailed. So this one will only have one critical value since we only have one tail. And it's going to be a positive because it's to the right of 0. Okay, so we're going to be doing, since this is a test about proportions, we're going to be doing using the z-scores. So this boundary right here, the critical value, is going to be a z-score, and it's going to be positive. Does that make sense to you? Okay, so it's going to be a positive z-score with an alpha area of 0.05 to its right. Now, you mentioned that you weren't sure what to use, Excel or a table, or you can use StatCrunch too, but for certain things. But when dealing with z-scores, most of the time, I just teach students to use the table to keep it simple, but you can also use Excel for this. So if we use the table, let me open up. Do you prefer to use? Okay, well, using Excel is fine. It's not a problem at all. And it's actually pretty easy. So if you've been practiced with it, you might feel more comfortable doing it this way. So the significance in the left tail is, or was it right tail? Right tail. Well, either way, we have an area of 0.05 in a single tail. So the z-score, the critical value that it is a z-score, we will use norm dot inverse. Now, norm dot inverse always needs a left tail, left probability, a left area. So it's going to read this as if it were in the left tail. So it's as if it's as if um, the calculator, if you tell it, if you tell the Excel 0.05, it understands it over here. So then it gives you a z-score that is negative because it's to the left of 0. But so notice that right here, I got a negative critical value, a negative z-score. But I would know that that should be positive because my z-score is on the right. So it's the same absolute value, but it's positive. Does that make sense? Or if that bothers you, you can also think about what's the area to the left of this boundary. If the area to the right of it is 0.05, what's the area on the other side? That's okay. I'm only asking so that I can figure out where you are. So the entire area under the curve is 1. So if I have 0.05 over here, then all the rest of it is on the left. So that would be 1 minus 0.05. So I can even put that in here as my probability. I can put 1 minus 0.05 even like that if I wanted to. And it'll see how it gave me a positive now? Yeah. Whoops. If it's if it's an area that is greater than zero point 0.5, meaning greater than half, it'll come out positive because it'll be on this side of 0, it's half of 1, right? So this whole area under here is all half. That's 0.5. So as soon as you get, that's right. So if I subtract 0.05, I'll get 0.95 on the left. But I mean, I've taught you guys to use symmetry. So what I normally do is I just put in the 0.05 and I see what the value is, and the absolute value is what's important to me because I know that the curve for z-scores is symmetric. You know, if I have negative 1.645 over here, oh my gosh, I'm sorry, my pen is like, yeah, it is kind of, and I've actually gotten a lot better, but it's still stinks. So if I have this over here, then I know I have the twin over here. So yeah, correct. So I always do that, and then I just look at my sketch and I go, oh, it was a right-tailed test, so that has to be positive. Yeah, if it's on the right. If it's on the right, if it's on the left, then you would want it to be negative anyway. And if it's a two-tailed test, then you'll have, both. All right, so then you have your critical value is positive 1.645. That's part of the problem. And I think it said round to 2 decimal places, so that would actually round like this. And then the p-value is the area that goes along with your test statistic. So they gave us, just like they gave us the significance level, and we were able to use that to get to our critical value, they also gave us the test statistic. And we need that test statistic right here to find the p-value, because that's the test statistic is the boundary for the data. There's 2 sets. So now I know what the boundary is. It's right here about, and it's 1 point, I don't have enough space there. Let me see. So this little boundary is 1.11 to z-score, and the area to the right of that is the p-value. P for probability. Prob prob right. So now you have a z-score, and you can go in and use with a test statistic of z equals 1.11, or I should do it like this. I can find the p-value by doing norm.distribution, and it wants a boundary. The boundary is this. The mean is 0, the standard deviation is 1 because they're z-scores, and yes for cumulative. So this is the left-handed area, but I want the area on the right. So for this, I would want to subtract that from 1. Yeah, because when I use norm dot distribution, it always gives me the area to the left. So what that gave me before I subtracted it from 1 is not the p-value because it's this point 0.8, what was it, 865 or something? 8665, yeah. So that's this area all the way to the left, but the p-value is on the right. Exactly. Yes. You can also, there's, if you don't want to have to think about that, I mean, to me, it's obvious when you do this because that's a big probability. That's close to 1. I'm expecting something that's at least less than half because it's on only one side of 0, right? So I'm looking at that number and I'm going, oh, that's got to be the other side of the boundary. The side that I want is the smaller side. So I'm going to do 1 minus that. And then I know it's 0.1335. Okay. You can also, if you feel better about it, you can also change the boundary to a negative, and then it'll just give you the left tail. I don't know. Maybe that's more confusing. I don't know. There's a lot of different ways. Yeah, you can do it that way because then what you're really doing is you're flipping your picture. You're doing the mirror image of your picture like this again. Even though it's on the right, you understand that everything's symmetric. So you may have you may have been thinking that way for test 3. And if you're using the z-score table, that's definitely how you want to think because, using the negative side of things. So if you have this picture over here with a boundary of 1.11 and you're looking for this area, then you can think of it as the mirror image, whoops, on the left with a negative z-score, and this area is going to be the same amount. So because that's how the norm dot distribution is set up, it's convenient to do that. You see, and then it just gives it to me that way. And then if you're using the z-score table, yeah, that's right. That's that's how I teach it. I teach it just the left side because everything's symmetric. So, yeah. Yeah, so now that you understand it, if you go in here and you look up a z-score with the same absolute value, even though it's negative in here, here's negative 1.1, and the last digit was 1, so it'll be in this column and this row. So it's 0.1335. And so that could be on the left or it could be on the right. It's the smaller tail is the thing. It's always the smaller tail. When you get anything out of this table, it'll always be the smaller tail. Yeah, well, because it's only one half of the picture. So you're only that table only goes with areas up to here. So every single area you pull out of that negative z-score table is going to be a smaller tail. Yeah, so when you look at your picture, whatever you got out of the table, label the smaller tail with that area. Yeah, so now we have the p-value. That was it. Now there is a curveball though with some of these questions. So let me get to that in a moment, but let's put this down, 0.1335. Did I close my, oh, no, no, no. Oh, I see. Because I'm still getting used to some new things. It just was updated. Okay, there we go. So yeah, we were trying to just answer this part of the question. So the answer was 0.1335. Okay, so, and I always have to check because I also transpose things, like I'll mix up my numbers. 0.1335. Okay, so that's done. Now, there was a similar question that we did in class today, and I don't know if you caught it, but another student had asked almost the exact same question you asked. So let me see if I can pull up that question. This is the one you and I just did. That's a different question. Here we go. This is it. This is the question that somebody else in your class asked. It looks the same, right? What's different though is the claim has the equal sign in it. Correct. And that's why we have not one but two critical values. And you have to be careful because when you set it up, you see how we had to split up the alpha? They gave us an alpha of 0.01. So half of 0.01 is 0.05. We had to split it up. Normally you don't do that if it's a single tail. You just put everything on one side. But here we're putting half on one side and half on the other side. Then we found our critical values. And then when we found the p-value, the trick is just like the alphas are split up in half, once you put your test statistic on the image and then you find the attached area, that only counts as half of your p-value. Then you have to double it for your total p-value. And that only happens with two-tailed tests. Otherwise, your p-value, like before the question that you and I just did, we did not double the p-value. We took that area that we got out of the table and out of Excel, and that was it. That was the answer. We didn't have any more steps. So from the beginning, if you want, we can just do this one from the beginning. All right, so we start off with the claim. The claim is The claim is that P is equal to 1 over 5. So the null hypothesis is now going to contain the claim. That's the claim. That means that the alternative hypothesis has to be the complement of the claim, kind of like the opposite, slightly different concept, but close enough for our purposes right now. They have to complete each other. They can't have any overlap, and they have to complete all the possibilities. So complement is part of the word complement is from complete. So then we have a two-tailed test. So when we set this up, we know that we're going to have two critical values, one over here and one over here, with the same absolute value, but just different signs. And the area in each of these tails is going to be identical, and it's going to be half of the significance level. So half of the significance level is 0.05. Yeah, yeah, zero point 0.1. So yeah, you start like this, and then you take half of it. And if you have to actually do that in a calculator, that's helpful sometimes. Yeah, so that's how we got the 0.05. Now that we have that, we can use it to find the critical values. The easier one to find is the negative side. Also notice that this is a p-test, and so since we're testing a proportion, this is z-scores. If we were testing a mean with sigma unknown, it would be a t-test with t-scores. Yeah, so anytime it's a claim that involves a proportion with the letter p, that's going to be a z-score. If it's a claim about a mean, then you have to be a little more careful about whether you should be using z or using t. And the way you tell is if you have the true population standard deviation, you use z-scores, and if you don't, if you just have the sample standard deviation, then you use t-scores. Okay. So for this one, we're using z-scores. We're now looking for a z-score boundary right here. And we know this one's going to be negative, this one's going to be positive, but we have an area of 0.05. So we can use Excel or we can use the table, or you can do both, which is probably what I would be doing just to have the extra practice. Now the area is still 0.05 in one tail. So I know that that area to the left of it is going to be negative 1.645 again. And if I was looking that up in this table, I would start with the area, which is on the inside of the table. 0.05 is in between these two. So it has that special value that leads us down to here. Yeah, good. Yeah, so good. So then that's our critical value on the left and on the right. We have two of them this time. So when you go to enter your answer, notice it says the critical value or values are, and then you use a comma to separate the answers as needed. So because it's a two-tailed test, I'm going to enter negative 1.65, comma, positive 1.65. All right, now the p-value. I'm going to look for the test statistic given in the problem, right? It's a z-score, negative 1.08. So that's somewhere in here, negative 1.008. So this has a boundary leading up like this. I'm just going to erase some things here because I don't guess we really need that anymore. The p-value is the shaded region in the smaller tail but it is half this time. That's right. So now I can go back to Excel if I can find it. There it is. And put in my test statistic of negative 1.08 and use norm.distribution again. The boundary the mean of a z-score, the standard deviation of a z-score, and yes for cumulative. So I'm getting, that's half of my p-value now though, because this is a two-tailed test. So then my whole p-value is 2 times that area. Yeah, it only gives you the one tail, and then your total p-value is 0.2801. Yeah, so the 0.1401. I'm just having just a lot of trouble going back and forth. Let me try to put this on here. Point 1401. That's that area there. But the total p-value, that is my answer right here, is the doubled amount, both tails, right? Okay, exactly. Good. And I find that that is one of the areas that's usually the most troubling, is knowing when this is going to give you half the amount or the whole amount. All right, so um, can you think of anything else specifically? I mean, we talked about how you choose z-scores for proportions tests. You always use z-scores for proportions tests with, any kind of, when your claim is about a percentage of any kind, it'll be a z-test. But when it's an average that your claim is about, it could be a t-test, and most of the time it's going to be a t-test because you won't know the true standard deviation. This was a z-test, or a normal test, however you want to call it, but this is where we had z-scores. And one of the ways that I encourage students to try to keep it straight if you have trouble remembering is to look at the formula packet reference sheet, because notice that you have all these categories. You have hypothesis tests for a single sample mean where sigma is known, and then you're using z-scores, right? And then you have a test for a sample for a mean where sigma is unknown, and then you're using t-scores. And what was the difference between these two? It was that we knew sigma and we used z-scores, or we didn't know sigma. Instead, we only knew the sample standard deviation, so we used t. And then, yeah, yeah. And then the proportions tests always use the z-score. There's no other option. Uh-huh. We were just doing a proportions test, except for we didn't have to use the formula because they already gave us the test statistic calculated. So there's no sigma. When it comes to proportion, oh, so alpha is another Greek letter, and that represents your significance level. But that doesn't, yes, and that doesn't have, that's okay, but that doesn't actually determine whether you use z-scores or t-scores. It just helps you find the position of the critical value, not in choosing the sampling distribution. The choice between Z or T is only if you're dealing with means. That's the only time you really think about it. If you're doing a test about a mean, then you have to choose between the two. Otherwise, you just, if it's proportions, you don't even have to worry. You just go right for the z-scores. And then you have dependent or paired data, where you create a list of differences and you get the average difference. And that's always a t-test. And then we just started doing chapter 9. That's part of chapter 9 right there. But the other part of chapter 9 is two independent samples where the data is not paired. And then you're doing the exact same thing again. You're going, oh, I'm doing a test about some means here. There's, instead of one mean, there's two, but you still think the same way. If you know your sigmas, then you use z-scores, right? If you know the true population standard deviations, then you use z-scores. If you don't know the true standard deviations, if the sigmas are unknown down here where you only know the sample standard deviations, then you use t. That's right. So again, notice that this is two proportions. And again, we go right for the z-scores. There's no choosing between z and t. So when you have z-scores for your critical value in your test statistic, notice that we were using norm.inverse, or if we're looking for an area, norm.distribution, right? If it's a t-test, it's almost exactly the same, except for instead of using norm distribution and norm inverse, you'll be using t.inverse. Does that make sense? Mm-hmm. Yes. Yeah. So this is norm, right? And that went with, oops, I didn't mean to change that. That went with the z-score formulas or the z-score table, right? That's norm. But if it's a t-test, then you're using this table, right? T-distribution, or instead of, like I said, instead of using norm.inverse, you would use t.inverse. And you just have to tell it, instead of telling it a mean and a standard deviation, you tell it degrees of freedom, and that's always n minus 1. Do you know it? Yes. Mm-hmm. It's always n minus 1. And if you forget, notice that it's on here. Degrees of freedom n minus 1. And also down here for paired data, same thing, n minus 1. And also down here for two independent samples, notice though that it says the degrees of freedom is the smaller n minus 1, because you're going to have two separate samples. So you'll have two separate sample sizes, and sometimes they will be different. You always go with the smaller one. Hmm. And it also tells you to use not pooled if you're doing it on a calculator. So everything's on here. It just takes getting used to what these things mean. But it's kind of like if you had a certain set of recipes that you were going to use, you would always pull out your recipe card and try to see if the ingredients match. You know what I'm saying? And then also up here, you see where it has these little references like this? I don't, yeah. So I don't know if you have one of those or if you even want to bother with that because it's just another thing to learn, but some students like those. So you mhm. Yeah, and it's easier too if you have actual data that needs to be entered into the calculator. You don't have to type it in by hand because you can make mistakes typing in your data. With Excel, you can actually open it, copy and paste it right into the spreadsheet. There's also StatCrunch, which is basically like having a TI 8384 calculator, but it's just on your computer. But I think Yeah, and I did some demonstrating with that today, although it was a little crazy because I had some technical difficulties. So I'll probably try to do a couple more of those on Thursday, depending on what kind of questions I get. I'll probably do at least, one more. But, StatCrunch is really user friendly. It's, what was I going to say? It's really useful. It's really easy to figure out, and if you can't figure it out, or if even before you try to figure it out, the tutorials are under Tools for Success in Pearson. So if you go into Tools for Success, let's see how long it takes to load here. And you scroll down, you see where it says StatCrunch. StatCrunch video tutorials. And they're all organized by topic. So if I'm trying to do I guess the hardest part is knowing which one of these you're supposed to look at. But yeah, so like for this one we were just working on, we were doing a hypothesis test, right? For not a mean, but a proportion, and it wasn't raw data, it was summary data. Or was it a proportion that we did? Yeah, we did a proportion, and it was summary data. But so this will walk through how to actually do it if you were doing a whole hypothesis test, right? This question was not us doing a whole hypothesis test. This question only required us to use a certain area to find a boundary and then to use a boundary to find a certain area. Yeah, I think it's really valuable. It just, I guess maybe it scares people away at first, but I, yeah, so I'm not sure how to um, make it seem more friendly, but I tried to give it more colors. That didn't seem to work. So, um, you know, this one. Yeah, yeah. And the other one has the exact same stuff on it. It's just organized a little differently and it's less colorful. But, but, well, it might. I mean, I'd like to know if you try to use the old one and you try to use this one, if this actually makes a big difference for you being able to follow and understand what's going on. Because yeah, 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 and but it's also I should point something else out to you while I'm thinking about it. It only has, so here's the older one. And I have a bunch of examples posted in the previous semesters folder where they're actually filled out. Um, but like the one that you and I were just working on is only this part of it. It doesn't have the confidence interval side of things. Um, it's I have it organized as a separate page now. But anyways, there's a second part of it, which is confidence interval. And you just have to be careful with the confidence interval. The easy thing to remember with confidence intervals is you always use the same critical value and it has to be positive. And what happens is that if it's a single-tailed test like we have right here, and your confidence interval is always two-tailed, then you have to double up on your significance level. So if I was going to do a confidence interval to go along with this hypothesis test, I would have to do it with an alpha of 0.1. I would have to double this right-hand side. I'd have to do another side. So then it would be a 0.1 significance level, which would make it a 90% confidence level. So a lot of students will look at this and they'll go, okay, the confidence interval should be 95%. But it shouldn't be 95%. It should be 90% because you have to double this area. Only if it's a single-tailed hypothesis test. If it's already a two-tailed hypothesis test, then you already have two tails. That was another place that people got tripped up a lot. And this is the reason that I have this section where you are supposed to think about the confidence level for the confidence interval. It's not always as obvious as you think. It trips up tutors as well. Tutors will get that messed up, and they'll be so frustrated because it doesn't make sense. You go, oh, it's an alpha of 5%, so obviously this should be a 95% confidence interval. Nope, not if it's single-tailed. If it's a single-tailed hypothesis test and you're doing a two-tailed confidence interval, you have to match the two tails. I don't know, this might be too much information for you all at once, but good. Well then, if you don't have any other questions in mind, maybe we should break and let you do some more practice, and then you'll know what kind of questions you have remaining, and you can send me some for Thursday. Yeah, and I know